prior to spring break, we actually had our Module 2 exam. So we're transitioning into Module 3, which is carbon-carbon bond formation via substitution at the alpha carbon. And so what we're specifically going to look at is the formation of a nucleophile called an enolate. Then we're going to react that enolate with different electrophiles at different oxidation states. So the first board here that I'm going to write is the big picture of this module. And again, you have a homework set, quiz, and an exam 3 bonus, all open in Wiley Plus right now that you should be working on. And those will close on April 13th according to the existing due dates. And then you'll have your Module 3 exam through Wiley Plus, and we'll talk a little bit more about that as the weeks go on here. So, not seeing any questions, I'm just going to go ahead and get to it. Again, most of this stuff is on my YouTube channel as well, in shorter screencasts if you want to review it. And this is being recorded, so you should be able to watch it later, but I make no guarantees. So we are looking at substitution of the alpha carbon. So that's the big picture for this module, and really it's about formation of carbon-carbon bonds primarily, but we will look at carbon heteroatom bonds as well. So again, use the chat function if I'm going too fast or you want something re-explained or the camera doesn't look right. So let's consider the following substrate. So we have this carbonyl functionality. So again, carbonyl is CO pi bond. I'm calling this side of the molecule R. And R can be the following things: H, so if it's an H, it's an aldehyde. It's a carbon, it's a ketone. And this is the one that we'll have to pay special attention to moving forward throughout this. I'm going to draw a dotted line here because these are just oxidation state 2 functional groups, but this chemistry will also work for oxidation state 3, where we can have R being OH, that's the acid. We have OR1, that's an ester. Or we can have nitrogen, so R1, R2, that would be an amide. And again, these would be oxidation state 3 compounds. So let me point out some things in this molecule that are particularly relevant to this chemistry. So we've identified the carbonyl. The carbon right next door is the alpha carbon. Then we have beta, gamma, and delta. So we're really specifically concerned with the alpha carbon because relative to these other ones, these hydrogens have increased acidity. So if we treat this compound with some base, I'm just going to say B with a lone pair for now as the base. We're going to look at what specific bases we can use to carry out this chemistry. So what will happen is the base will extract an alpha proton. I'm going to push arrows like that to show the lone pair being delocalized onto the oxygen. So in this process, we lose conjugate acid of that base. And the formation of this thing is called an enolate. So where does this name come? We have an alkene, that's the ene. The OL is from a deprotonated alcohol, that's why it ends in ATE, so olate, so enolate. Again, this is going to be a nucleophile. So with all of these different functional groups, depending on what base you treat them with, everything's always happening at the alpha carbon. The base will always deprotonate alpha hydrogen. So that will generate an enolate for all of these things, depending on what R is again. And then really what we're concerned with, I'm going to show this sort of branching off. We have a nucleophile, and here we're going to look at different electrophiles. And we're going to classify the electrophile according to the oxidation state. In the first one, if we're at oxidation state 1, we use this compound, the 2-iodopropane. This carbon is bearing a sigma bond to a heteroatom, so it's at oxidation state 1. We plug in our lone pairs, we have delta minus, the carbon is therefore delta plus. So we can draw a resonance form of this enolate, where we're actually showing the negative charge residing on the alpha carbon. So this negative charge will attack this delta plus, displacing the iodide. But overall, that's an SN2 reaction mechanism, which we learned in 255. So what are we doing? We removed this H originally, substituting it for this carbon backbone. Again, we still have a remaining H. Now this is the new bond that we formed right there. Alpha carbon. So it formed, we have 1, 2, 3 carbons. It's bonded in the middle. We said along this original chain we had beta, gamma, delta. Now what we're forming, we formed that bond. This is our new beta carbon. So I don't see any questions in the chat. Hopefully y'all can still hear me and see this just fine. So let me just reiterate that. Every reaction that we're going to see, the new bond is always formed between the alpha carbon and the new beta carbon. What's changing is the nature of the electrophile that we used. So in this case, this oxidation state was 1, the iodide was displaced. Now the oxidation state at beta prime is 0. So overall, it's a reduction in terms of the electrophile that we started with. So this reaction with oxidation state 1 is specifically called an alkylation. So is anyone else's audio cutting out in the chat there? We did some of this stuff as faculty last week, and the audio wasn't the best. So really, I think it's an issue of internet streaming capability here at USM. And most of these are posted on YouTube if you find you can't follow what's happening here. So let's go up in oxidation state and look at a different electrophile. So specifically, we're going to look at aldehyde. This is at oxidation state 2. I think I'm talking loud enough to trigger this thing to capture the audio. But again, I think it might just be a bandwidth issue. So just keep that in mind. So the nucleophile is going to attack the electrophilic carbon here. And again, we've seen nucleophiles add to carbonyl carbons, form the bond between the alpha and this carbon. This is then a nucleophilic addition. So our original backbone stays the same. So this is the bond we're forming. This is the carbon bearing the carbonyl. And here's our new bond, C alpha, C beta prime. The reduction has occurred from 2 to 1. The name of this reaction up here, again, that was alkylation. This has a different name, called an aldol reaction. And then we're going to look at one more electrophile. So we've gone from 1 to 2. We'll look at oxidation state 3. So if we look at, say, this compound, which is an ethyl ester. So this carbon here, oxidation state 3, it's going to go to oxidation state 2 in the product. So what's going to happen, this will add to that carbon. We'll get a nucleophilic addition and then an elimination. So we've gone from 2 or 3 to 2. So this reaction is called a Claisen. Again, here's the new bond that we formed. We have alpha, beta, gamma, delta. Here's our new beta prime. So again, the bond we're forming is always between alpha and the beta prime. Okay, any questions on this first board before I go ahead and erase it? Give you a second or 2, 3. Maybe write something in the chat. Or if you feel brave enough to unmute your microphone, shout something out. It looks like we have a decent amount of people online here. Yeah, I don't see any questions, so I'm going to go ahead and erase this. And that was the big picture of what we're going to be doing. We'll look at these different reactions in different contexts. So what we want to do now is understand why the alpha carbon is acidic. So we're going to look at carbon hybridization. We have an sp3 hybridized carbon. sp2 hybridized carbon, and then sp hybridized carbon. So if we recall from our acidity studies, the sp3 hybridized carbon CH bond has a pK of about 50. So it's important to remember that in relation to specifically the alpha carbon. sp2 pKa was about 44, and sp pKa is about 25. So why am I bringing this up? So remember that the larger this number, the less acidic the CH bond. So if we examine that general compound that I had on the prior whiteboard, again, R can be pretty much anything. Here's the alpha carbon. We can see that that alpha carbon is sp3 hybridized. None of the prior chemistry on that whiteboard would work if the acidity of these hydrogens was 50. They're significantly lower than that. In fact, they're about 20 to 25. So they're much more acidic due to the fact that they're next to this carbonyl. So let's examine that deprotonation event again. So I'm going to say these. And the reason this is a range is because it depends on what this R group is. So from aldehyde to ketone versus esters and amides and those things. Aldehydes and ketones are typically closer to 20. The esters and amides are a little bit higher at 25. So again, we're going to look at what specific types of bases we need to use to carry out this reaction. But again, the base applies the electrons that will abstract the hydrogen. Grab that hydrogen, we're going to break this bond and put the electrons right on the alpha carbon. So we lose the conjugate acid of this base. We still have a remaining hydrogen. There it is. Then we have our negative charge. So we have a carbanion. Carbanions are pretty reactive intermediates. However, due to the proximity of this carbonyl, we can delocalize that lone pair onto the oxygen, so that stabilizes it. That's why this acidity drops so much from 50 to this range here. And again, here's our resonance arrow. And again, this is our enolate, the carbanion. Which means it's a nucleophile. So the nucleophile is supplying the electrons to form the new bond. So what else do I want to say about this? Again, I can't stress enough that everything in this module what you're going to see in the homework, the quiz, and the exam is everything is taking place at the alpha carbon. So how can we ingrain that into our thought process here? So again, this is the rest of this chain. This beta carbon has 2 hydrogens as well. These hydrogens resemble the acidity of a standard sp3 hybridized carbon. So the pKa of these hydrogens are 50. The reason for that is there's no stabilization that you see, the beta, the gamma, or the delta. It always has to be a hydrogen next to a carbonyl to reach this acidity. And that's where the substitution is going to take place at the alpha carbon. So let me, I don't see any questions. Let me pull a problem from the book here. A couple of structures. Again, if you have questions, you can unmute your mic and ask, or you can put it in the chat. If you guys, if the audio is really crappy, I'll try to look into a different sort of microphone. Maybe that might work. We're going to look at problem 21.4, part A. And the question states, draw both resonant structures of the enolate form when each of the following ketones is treated with a strong base. So I said in the prior whiteboard that ketones were the special case that we have to consider because all the other functional groups only have 1 alpha carbon. Ketones can have 2. This ketone in particular is symmetric. So here's an alpha carbon. Here's the other alpha carbon. Due to the symmetry of this molecule, alpha and alpha are the same. If the ketone is not symmetric, you will have 2 different alpha carbons. And that's when you have to really think about the choice of base, because you can generate at that point 2 different enolates. So this question is asking us to draw the enolate formed when a deprotonation happens. So if we treat this with base, there's the arrow pushing to show the enolate. We now have 1 remaining alpha hydrogen there. This alpha carbon remains unchanged. So a resonance form of this enolate, we're just pushing the electrons back. So let's look at question B, part B. Again, this entire problem is just specifically, well, I guess it's not. Most of these are ketones. Problem E is an aldehyde. So we're given this structure. Maybe let's see if we can make this interactive. So given this ketone, as fast as you can in the chat function, how many alpha carbons does it have that are bearing hydrogens? Just All right, all right, all right. Seems like one is the winner. So I think this specific substrate illustrates a good point in terms of how we talk about these structures. So again, it's a ketone. We have an alpha carbon. We have another one, but we're going to call this alpha prime. So alpha prime has two H's. So there's only one alpha carbon bearing hydrogens. This alpha carbon is what we call non-enolizable. So when we treat this compound with a base, the action is only going to happen here. So we don't have to worry about anything happening at alpha because it's bearing two methyl groups. So in a sense, when we treat this compound with a base as well, our job is pretty much easy in that we understand only alpha prime can do a substitution. Again, the issue, it gets a little tricky when both alpha carbons are enolizable, but they're not the same. So if we draw this enolate, so there's the enolate form, resonance form. Put the negative charge actually on the alpha prime carbon there. So that's one skill that you need to be good at during this module, is just identifying the alpha carbon and if it's enolizable. So we'll run through C and D real quick here. So those are the structures of C and D. Again, they're both ketones. You can see similar to B here. The alpha carbon, as drawn, both of those alpha carbons are non-enolizable. So this is sp3. It's completely blocked by methyl groups. There's no hydrogens. This is sp2. Completely blocked. There's no hydrogens. So therefore, the alpha prime, there's three acidic protons here. Alpha prime, there's three acidic protons there. That fact will be important to us when we look into the aldol reaction specifically, as you get mixtures of products, and we want to minimize the mixtures. So as one of the components, we can use a ketone that's non-enolizable. So we'll just quickly look at E because it's an aldehyde, just so you can see the difference. So we have this compound here. I would say this is 2-methylpropanal. Again, the carbonyl is bonded to an H. This is not an acidic proton. This carbon is bearing one hydrogen, so there's only really one alpha carbon. This, like we said, aldehyde, carboxylic acid, ester amides. The thing bonded to the carbonyl is not carbon. We really only have one alpha carbon to deal with. We have a single alpha hydrogen. So if we treat that with base, we would get the following enolate. So So again, our alpha carbon resonance form. So the nucleophile supplies the electrons to form the new bond between alpha and beta prime, the new beta carbon. So what we'll do next, I'll go ahead and erase this. What we'll do next, we've really already seen how an enolate is formed with base. We'll now do it under acidic conditions. And then we'll look at some more substrates to identify acidic protons. So if we're under acidic conditions, we form a neutral enol. The things I was showing you prior are called enolates because they have a negative charge. So let's consider the following substrate. We have this ketone. So we have two different, we have alpha, we have alpha prime. This has two methyls, one H. This has three H's. Let me just draw those in. So we can see that alpha and alpha prime are not equivalent. If we treat this now with some acid, so again, we'll look at different types of acids, but this is the general arrow pushing mechanism to form an enol. A carbonyl with acid is protonated. We can show a resonance form for this, where the plus charge is shown on the carbon. So again, this is a resonance arrow. This is the conjugate base of this acid. And what it's doing, aside from balancing out the charge, it can act as a base to extract this proton. So we see now that we're neutral. So in this process, we lose or regenerate the acid. So the acid is a catalyst. The neutral species is called an enol, and there's no ATE charge because there's no negative charge on the oxygen. So acidic conditions generate enols. Any questions on that mechanism? Don't see any, so someone's typing.
Not yet, no, thank you.
the question is, so does the conjugate base take the proton from the carbon with the fewest hydrogens? So specifically, we're going to look at different bases, but that brings up a good point, because basically we're looking at where alpha prime has one H, alpha has 3 H's. So maybe let me draw, I won't draw the mechanism. What I'll draw next to this is if we enolize from alpha, and then we're going to compare, and then I'll ask you guys a question. So again, in this route, we were enolizing from alpha prime. So if we go through a bunch of steps, same sort of thing, and we enolize here. So this is the complication when you're actually starting with non-symmetric ketones. That you can enolize from either alpha carbon, so alpha or alpha prime. So let me ask you a question, see how fast you can type. You're forming two different enols. Number one, what is the relationship between those enols? Number two, which do you think is the most stable and why? So maybe take a minute or so to consider those. So Allison asks, is there a rule for labeling alpha and alpha prime? I don't think, not really. There's no rule. I think it's just completely arbitrary on my point. Whatever you do, however you label it, just be consistent through your mechanism. So again, the question was, what's the relationship between these two structures? Of those two, which one do you think is the most stable and why? So Ireland put in her chat response here. The first one that we drew.
How do you like turn it off?
This is the most stable because it's the most substituted. Again, if we're counting, we have 1, 2, 3, and if we count the OH, that's 4 substituents. Here, if we're not counting hydrogens, we count 1, 2. So this would be a disubstituted versus tetrasubstituted. So this is more stable. And the relationship between these two is constitutional isomers. So this is, I would say, in this module 3, to me, this is probably the most difficult thing to keep track of when you have these non-symmetric ketones. Because not only can you form different enols or enolates, but we'll look at substrates where, like if these groups here, these groups are both methyl. So when this comes out at the end, you can, if they're not the same, you can get geometrical isomers. And so that adds another layer of complexity to this. So this is probably the most complicated thing for the module is understanding the ketones, the acids and bases involved in which preference of enol you're forming. So, any questions on that? On the acidic mechanism? So I'll briefly go through this again under the basic conditions to form an enolate, just so you can see that and how it relates to a specific topic. That'll be important moving forward. So enolates form in basic media. Here's our ketone that we were just looking at. So if we're treating this with, say, sodium hydroxide, so there's a base. So it's abstracting the alpha proton. We're going to form the negative charge on the oxygen as we push these arrows. So now we have this sodium counterion. It's in the negative charge here. So again, this is an enolate. And that refers to this negative charge. So why is this important? Both enols and enolates. Let's consider the following. Reaction. So if we look, we have a ketone, we have, say, alpha prime, and that's, again, just arbitrary on my part. This is non-enolizable, so nothing's happening there. Alpha prime has one enolizable hydrogen. So this compound, maybe let me ask you a question. What's the stereochemistry of alpha prime? You want to just put it in the chat box. And what is, using the Kohn-Ingold-Prelog rules of assigning stereochemistry, what should alpha prime be? We've got quite a few R's showing up, so it is R. So the stereochemistry is R. And if you're starting with this specific compound, the specific rotation, the specific rotation as measured experimentally is plus. So you take this, you make a solution, you put it in a polarimeter, you get the dextrorotatory sign. If you treat this compound with sodium hydroxide under basic conditions, or alternatively, if you treat it with acid under acidic conditions, this center, which is R, as that rotation, undergoes racemization to form a racemic mixture. So you will end up with 1-to-1 mixture of the R. To the S. So this is a racemic mixture when it's 1-to-1. Again, it's not going to have any optical rotation. The value of the optical rotation will be 0. So if you're starting with R, you end up with 1-to-1 mixture of R and S. And the reason for that is if we look above, say in this example, why this is important. Any alpha carbon we're starting with must be sp3 hybridized. It has to be. Another stipulation of this chemistry. We need sp3 hybridization to have the acidity. When the enolate or the enol forms, the hybridization changes to sp2. So a similar thing is happening down here. I'll draw the intermediate when this thing enolizes. They were under basic conditions. So we see it again. This is now sp2. So what do we know about sp2 hybridized carbons? So it's trigonal planar. It's flat. So what's happening in here is you form the enolate. From here, it's forming this and this. The proton that's reforming at the alpha position can attack from either face of that flat enolate. So there's no facial preference. These electrons come down, these come off. Protonate. So to reform either of these, if the water is coming from this face, you would get that stereochemistry. The protons coming from the front. Water's coming from the back. You would get the S stereochemistry, and both will happen equally. So under these conditions, either basic or acidic, you get racemization at the alpha carbon. Any questions on that before we move on? So I'm going to pull some problems from the end of the chapter now, just so we can apply these concepts and you can see them in different circumstances. This compound is called ethyl. There's the ethyl. It's an ester and a ketone. This compound in particular is going to be pretty important to us a little bit later on in this chapter. But its name is ethyl acetoacetate. And let me ask you a question before I write it up there. How many alpha carbons do you see? Just write a number in the chat box. Once we get some of that, we'll explain that, and I'll ask a couple more questions. So the majority of you are typing in 2. So there are 2. So we have alpha and alpha prime. So I'm telling you that they're different, and hopefully you can see that as alpha has 2 H's, alpha prime has 3 H's. So this compound has 2 different alpha positions. Now my next question, of these 2, even though they're both alpha carbons, one of them is way more acidic than the other. And what that means is, if you treat this with one equivalent of base, you're going to get preferential deprotonation at one position over the other. So in the text box, why don't you type your choice, alpha or alpha prime, and then we'll talk about which one it is and why. So quite a few of you are typing alpha. So can you briefly explain why that is? Why is alpha more acidic than alpha prime? So a couple answers here. It looks like doubly stabilized. It's bonded to 2 carbonyls as opposed to 1. So yeah, that's essentially the correct answer. So this is going to bring up quite a few concepts here. So let's sort of go through it, take it slow, so we understand everything that's happening. So we know that 3 is greater than 2 from pretty basic principles here. So the alpha protons are more acidic because we can delocalize to this oxygen or this oxygen. So that's correct. These are going to be quite a bit more acidic. So these, we said a typical alpha carbon's 20 to 25. So these say, if these were 20, these are going to be about 10. So by adding this extra carbonyl, it essentially makes it, in this scale, 10 to the 10 times more acidic due to that double stabilization. So another way of describing this name, so this is an ester. If we're looking at this carbonyl specifically, and we label the chain, so we have alpha, this is going to be beta. So we're not considering my alpha prime here. So we have alpha beta. This compound is called a beta keto, so ketone ester. When you have these methylene alpha carbons sandwiched by 2 carbonyls, they're pretty acidic, and that's where the action happens preferentially. So even though there's 3 of these and there's less of these are more acidic. So that's important to realize. The next question I want to ask you is, regardless of this acidity, use some space in your notes to draw all the possible enols that you can think of for this compound. Regardless if you're deprotonating at alpha or alpha prime, draw them all. Take a couple minutes to do that, and then in your text or your chat function there, write how many you came up with. Then we'll circle back and write them all up here, just so you can see that when you have a compound where alpha and alpha prime are not the same, that you can get multiple enols or enolates. But let's specifically draw all possible enols. So we'll look at the enols, the neutral ones. And once you have them, write a number in the chat function, and then we'll draw them up on the board. So far, we have a couple people saying 3. A couple more people saying 3. So 3 is definitely, it's a good first approximation. So I hope this makes sense. Let me just ask the question and see if it does. If you're enolizing from the alpha position, of the 3, how many should I put there? If you're enolizing from alpha prime, how many should I put here? Hopefully that makes sense. Maybe type it in the chat box and see. So of alpha, how many should I put here? Like a couple people writing 2. 3 minus 2, that would put 1 there. Let's go ahead and draw this one first. So we're enolizing from the alpha prime position. So I draw this a certain way because when you have these beta keto carbonyl functional groups, typically what will happen, you get this hydrogen bond stabilization. So that's why I'm sort of drawing it like that. That means H bond. So yeah, this is, no matter which hydrogen you abstract, this is going to be the enol that you form from the alpha prime carbon. So we wrote for alpha, there's 2. It's a good first approximation, but I think there's actually more than 2. Maybe after we draw them up, you'll see why. So again, I'm drawing them sort of this way to demonstrate that hydrogen bond stabilizing it. So we enolized this way towards the ester. We can enolize towards the ketone. So again, the difference between these, or the relationship of these, are constitutional isomers. And we arrived at them by deprotonating either the alpha versus alpha prime. These we enolized a certain way. But I think maybe for each of these, we could maybe draw another. So we could draw another form for this and another form for this. So if you think about this bond relationship to this bond. What if when it enolized, the relationship was opposite? So now you no longer have this H bond, right? You can't form that H bond between this carbonyl oxygen and that hydrogen. I think maybe it'll help if I put this hydrogen in so you can actually see that. So these top two form that H bond. These bottom two cannot. So all of them are constitutional isomers, but these would be geometrical isomers about the alkene. Remember cis and trans. So this can have cis and trans, and that can have cis and trans. So we have a good first approximation at 3, but due to the nature of these groups, when you enolize from here being different, you can get cis or trans geometrical isomers. Again, with the ketones, that sort of complicates matters. Any further questions on that one? So it's about 2:07 now. So in the last couple of minutes here, what I'd like to actually put these enols to work in forming substitution at the alpha carbon. And what we're going to specifically look at is alpha halogenation reactions. We consider the following ketone. We have alpha and alpha prime, where alpha prime is the only enolizable hydrogen here. Alpha has 2 methyls. And we're going to treat this with trifluoroacetic acid. So that means we're forming an enol. And then we're going to react that in the presence of bromine. So this is our electrophile. So under acidic conditions, we are enolizing alpha prime here. So there's the enol. overall, this hydrogen is going to be substituted for a bromine, and that's what we're going to show in this mechanism here. So our nucleophile, our electrophile pair, this will come down, we reform the CO pi bond. The attack is happening at the alpha prime position. So we're forming a carbon-bromine bond. We then do a proton transfer, and we end up with our final product. Which we've substituted this H for bromine. So again, that falls under the substitution of the alpha carbon. Always happening, we're removing alpha CH bond, we're then substituting it for some electrophile, in this case it's bromine, so we've done alpha bromination. So another type of alpha halogenation that you'll see, this is a named reaction. The Hell-Vollard-Zelinsky reaction. This is a reaction specific to carboxylic acids. So if we take butanoic acid, again, this is what I meant by with these other functional groups. This is OH, so there's only one alpha position. So our job's a little bit easier. So alpha has two H's. One of them is going to be substituted. Nothing happens at the beta or the gamma positions because they're not acidic. Under these conditions of HVZ, we're treating with elemental phosphorus. Molecular bromine, and then we're doing an acidic, we're doing an aqueous workup. So we're substituting an H for a bromine. The phosphorus is there as the acid. That's what forms the enol. So we've formed two bromobutanoic acid. And that's useful to us for the following reason, because we can then take this, we can then treat it with an excess of ammonia. Ammonia is both a nucleophile and a base in this case. As a nucleophile, it's going to displace this alpha bromine. I'm going to write this in a specific way. As a base, it removes that proton. This is a byproduct you get. That's where the bromine ends up. So what is this? As we saw in the prior module, this is an alpha amino acid. Specifically, when we have the internal plus minus, that's called a Zwitter ion. So the HVZ reaction of acids is useful for making amino acids. And again, what we saw, what I circled in green there would be a side chain. Everything that's left over is the alpha amino acid part. So when you go on to biochem, the side chain is really what is changing. It can be acidic, basic, polar, nonpolar. Again, that was something we talked about before. This is the reaction to make amino acids. So given the time, it's almost about 2:15. What I'm going to do at this point is sort of wrap this up. If you have any questions, shoot me an email. If you want to provide feedback on this, send that in an email as well. Clarity of the whiteboard. I can see these reflections. I don't know if that bothers you or not. If I need to get a different type of microphone or whatever. But we'll meet again on Wednesday at 1 to 2:15 for the lecture. I'll also have an office hour with this conference thing tomorrow from 4 to 5 during the normal scheduled time. So we'll do the same thing again. But if you have any feedback to make this a better experience for you, let me know. Otherwise, please start working on your Wiley Plus stuff and some of the bonus stuff. Other than that, I'm going to go ahead and end this conference, and hopefully it will save it. And if you want to watch it again at some other point, that'll be possible. But other than that, stay safe out there, wash your hands, all that good stuff. And we'll see you Wednesday.